Let's take a look at recursive linear examples. So number one, the number of houses in a town has been growing according to the recursive rule. Here we have P of t equals P of t minus 1 plus 148. They give us an initial number, P sub 0 equals 213. Okay, so what is the recursive definition? It looks like P sub 0 is given. And then they have P sub n equals P sub n minus 1 plus d. This is the basic form that I'm seeing. And this is linear. So right away, we can see that the d value is 148. And the P sub 0 is 213. This is in fact enough to create the explicit formula. So let's take a look at the explicit formula right away. The explicit formula is P sub t equals P sub 0 plus dt. In the book it might be P sub n equals P sub 0 plus dn as well. But they just replace the variable with t for this problem. That's fine, we can handle that. So for this problem, P sub t would be P sub 0, which was given as 213, plus dt. And d is the 148. T. So this formula could be used to answer part A, but we'll definitely use it to answer part C and D. But with part A, if I were to let t equal 1, if I put 1 in for t, this formula would be P sub 1 equals P sub 1 minus 1, 0 plus 148. And we have P sub 0, it's 213. Adding these numbers together gives us 361. We have found P sub 1 using the recursive definition. Trying to erase, it doesn't seem to, there we go, it's erasing barely. All right, now if we let t equal 2, then our recursive formula turns into P sub 2 equals P sub 2 minus 1 is P sub 1 plus 148. And we just found P sub 1, it's 361. We add 148 to that, we get 509. So we are able to use the recursive definition to find these P sub 1 and P sub 2 terms one step at a time. The recursive definition is one step at a time. You can't jump straight to the 10 years. So for part C, I don't want to continue this process until I finally get to P sub 10, because that's going to take a while. Rather that, I have the explicit formula. I can just plug in 10 into that and work it out quickly. So that's what we would do for part C. P sub 10 equals 213 plus 148 times 10. And this works out to be 1,693. So all I'm doing here is just like 213 plus 148 times 10. No fancy business, easy to work out. Okay. Now, one other thing about the recursive definition, you can look at previous videos to see this, but if I start with my initial value, 213, enter, and in the recursive definition, wherever you see P sub t minus 1, if you use answer button, and then plus 148, this will recursively add 148 to the 213. There's our 361. If I hit enter again, it'll do another add 148 to the answer, which is 361. We should get the 509. So that's 2 3, 4, 5, 6, 7, 8, 9, and there's 10. So that verifies our work for 10. When will it be 1150? 10, 9, 8, 7, 6. Between 6 and 7. I can tell that from our work with this calculator. Between year 6 and year 7, we somewhere in between went to 1150. But that's not enough to round to the nearest tenth. So for rounding to the nearest tenth, we have between 6 and 7. Let's see what we get. So here we use the explicit model. So we're going back to the explicit model. But now this value is going to go into the p sub t. So we're going to get 1150 equals 213 plus 148t. So we have 1150 equals 213 plus 148t. And now we can solve this equation. Subtracting the 213, this will give us 937 equals 148t. And then dividing by the 148 gives us t equals 937 over 148. And now we can go to our calculator because they're asking us for the nearest tenth of a year. So we have 937 divided by 148. 6.3. Now, from our previous work, we knew it was between 6 and 7. Now we have a much more precise answer. We can round to the nearest tenth. Approximately 6.3 years. Okay, now pause the video while you work out question number 2. What you should get is p sub 1 equals 7,440. P sub 2 equals 7,530. The explicit formula is p sub n equals 7,350 plus 90n. The explicit formula for 10 years, we get p sub 10 equals 8,250. And the number of years, t, is, in this problem it's not t, sorry, it's n. N is approximately 42.2 years. All right, I hope this helps.